Hey gang, welcome to Computer Graphics. Today we are going to continue our exploration of lighting and shading. Specifically, we're going to continue looking at developing a model, a reflection model, or sometimes we call it an illumination reflection model that will allow us to more realistically render how our objects would look in a particular environment by modeling how those objects interact with the light in the environment. So that's what we're going to be doing today. We're going to be continuing this illumination reflection model that we started last time. Okay, so let me get started by pulling up my lecture notes. Okay, so just as a little bit of background, we were talking about the fact that our model will contain 3 different types of lighting or reflections because we're interested in the ultimate intensity of a point, because that's what we want to render, right? All of our little pixels are points on our objects, and so we have to figure out the intensity of that pixel, and really the intensity of the pixel is going to be the intensity of the light that's reflected off that spot on the object. And so we've said that we'll have 3 different kinds of reflections. We have ambient diffuse reflection. This just models background ambient light that comes in from all directions and is reflected from all directions. The second thing, and we just started talking about this one, is emitted light that comes from a point source, but that is diffuse, as in once the light hits the surface, it's reflected equally in all directions. And the last thing, we're going to be introducing this one today, talking about it in detail, is specular reflection. That's light that arrives at the surface from a particular direction and is reflected preferentially in a particular direction. So that's what gives objects, the specular reflection is what gives objects their shininess. That causes objects to have highlights on them. That's the specular reflection. Okay. So we have, and the overall equation that we're developing is this puppy. The intensity of the reflected light at some point, right, is the ambient background lighting and how that interacts with the object, and then the diffuse reflection and the specular reflection from every light source, every point light source I, summed over all of those light sources. And what we're doing basically is we're showing how do you compute ambient, how do you compute diffuse, and how do you compute specular, so we can plug it into this skeleton equation here. And I always try to be careful to point out that really, if you want to do full color for humans, since we're blind except for red, green, and blue color-wise, you just need 3 versions of this equation, 1 in red. I just put a red subscript on everything, 1 in green, and 1 in blue. So each of these 3 equations is exactly like this, except you're going to keep up with red light separate from how you're going to keep up with green light, separate from how you're going to keep up with blue light. And then in the end, of course, you have to put the red, green, and blue together to get the final color. And we had this little graphic that I didn't come up with. That's the link to it. By the way, all of the little images in here, if there's not a link or a credit, I created it. So, but anyway, this is the specular component. It's the highlight. The diffuse, which is, it's still, this part is brighter than this part because obviously we have a light source that's coming in this direction here, like at a 45-degree angle. So this is the diffuse point light source that's causing that. And then this isn't totally black. This is dark red, and that's our ambient term, our background lighting. Okay, again, we covered all of this last time, but I wanted to set the stage again. Ambient diffuse reflection, we normally just call this ambient. It is a type of diffuse reflection, but it's ambient diffuse. Ambient means the light's coming in from all directions, and diffuse means it's being reflected in all directions. So ambient light has to have a diffuse reflection. You can't have like ambient light coming in from all directions and then being preferentially reflected in some direction. That wouldn't make any sense, right? Because, you know, if light is coming in from all directions, it's going to hit the surface, and surfaces have some roughness, and that light's going to be bounced out in all directions. So we normally don't, even though this is technically ambient diffuse reflection, normally we just shorten it and say ambient, because there would be no such thing as like an ambient specular reflection or something like that. So if it's ambient, if the light is coming in from all directions, that's what ambient is telling you. Diffuse is saying, well, it's going back out in all directions. But there's no way that light can be coming in from all directions, yet going out only in one particular direction. So normally we just call this ambient. So how do you compute it? Well, the light's coming in from all directions, it's going out in all directions, so it's essentially directionless, so you don't have to worry about where the viewer is or lighting angles or anything like that, because there are none, or there are an infinite number of them if you want to think about it like that. So basically we compute ambient with a very simple formula. We say, okay, we have some constant that represents the intensity of the ambient lighting in the environment. Maybe the lighting, the ambient environment is 20%, or maybe the ambient lighting is 30%. But anyway, it'll be generally some percentage that'll say how much of the incoming light is this directionless background ambient light. And that has to be multiplied by the constant of diffuse reflectivity. Every object will have a reflectivity associated with it. If this were a color model, we would say that KD is the color of the object. If you're talking about a monochrome model, and this is a monochrome model here, it's the level of gray of the object. It's where it sits on the gray scale between white and black. Okay, so it's a property of the object. It is the object's color. If you want to think of gray as a color that goes from black to white. Okay, so the level of lighting in the environment times the color of the object will give you the ambient background lighting. Now again, if we want to really make it color, we got to repeat the thing 3 times, because we got to keep up with red light, green light, and blue light separately. Okay. And like I said, standard practice is to put these things in the scale of 0 to 1, and then at the very end, you need to scale it from 0 to 255, because that's how all this works. And again, I give an example here where a monochrome example and a color example. And so in the color example, let's say that the scene has a moderate amount of white ambient light. So the background lighting is white light, which means our red, green, and blue components are going to be equal. And I'm saying it's a moderate amount. So let's say 25% of the light in the environment is this background ambient light. And let's say we have a yellow object of medium intensity. Okay, a medium yellow object. And so yellow is red and green, but no blue. So 0.5 red, 0.5 green, and nothing in blue. So if you light this yellow object by this 25% intensity, after doing the multiplication, you'll get 0.125, comma 0.125, comma 0. So red is 0.125, green is 0.125, blue is 0. And then if you scale that, you get 20200, right? So 32320, because those are hex. Okay, is there any question about that? That was all from last time, but I wanted to run through it. Is there any way to determine the KD from a 6-bit hex? Any way to determine the KD from a 6-bit hex? KD, the constant of diffuse reflectivity, is given because it's a property of the object. So here I was saying we had a yellow object. So I had to give you the color of the object, right? So that's that. When you say 6-bit hex, we eventually convert this into, it's not 6 bits, it's a 24 bit color, because this is 8 bits, and 8 bits, 4 bits for each digit here. Okay, so you're mixing two things up here, Andrew. First of all, you don't algorithmically determine the constant of diffuse reflectivity. That has to be given to you because that's an innate property of an object. Just like I have to give you the vertices of an object. If I want you to know the color of it, I have to tell you. And the last thing is that we build the hex. When we're doing the computations, we normally keep everything as a percentage on a scale from 0 to 1. We end up, though, having to convert it by multiplying everything by 255 to get the hex. And color and grayscale, keeping, a lot of times I will introduce something with just one equation, right? But I always try to remind you that really, if you want to do a full color model, you have to repeat this 3 times, because you keep up with red light and red reflectivity separately from keeping up with the green light and the level of green reflectivity and blue light and the level of blue reflectivity. So whenever we're talking about light in the environment, that light will have some color associated with it. Now, the most common type of light that we have is white light. So if you're modeling white light, you set all of the red, the green, and blue equally, and that'll give you white light. But if you want to talk about the color of an object, like yellow here, I have to have, that's a constant of diffuse reflectivity. You have to have what it is in red, what it is in green, what it is in blue. And I'm just using yellow as an example. Any color except for red, for green, and for blue will be a mixture of red, green, and blue. So you'll have various values, for each of these color channels. Now, this little like red sphere that I showed earlier, you don't need a 3-color model to build that little red sphere, if I can find it, because red's really the only color we have here, except for white and the specular highlight. But and I have an example where I show that. But this is the only place where I'm mixing colors here. The rest of this you can use just a single intensity calculation, but put its result in the red channel and keep the other 2 channels 0. So really this is a monochrome model, except the highlight. The highlight there is white light, so there's 3 colors there. More of that will make sense when we do the model, but I need to move forward right now. Okay, emitted light. We're modeling that by point light sources, light coming in from a light source, hitting a surface, and then reflecting equally in all directions. It's called emitted point light source because we got an emitter, a single source, and it's a point light source. We model our light sources as points. So the light is coming in here from some direction, hits this point, and it's a diffuse reflection because it's going out in all directions. The upshot is we're going to have to keep up with the surface normal and the lighting vector, but we don't care where the reflection is or the viewer because there is no reflection. It goes in all directions. And that brings us to Lambert's cosine law. It's an interesting question. I don't know whether that should be pronounced Lambert or Lambert. And I've actually looked it up. And you think, oh, well, if he were French, then it would be Lambert. And if he weren't French, it would be Lambert, right? Well, Johann Heinrich, right, or Jean-Henri, he was Swiss, and actually where he lived is now part of France, right? So I don't know if and I do see his name frequently as Johann Heinrich Lambert, but also on the Wikipedia page they have Jean-Henri. So it's like maybe nobody is quite sure. Maybe he pronounced it different ways when he went to Munich. Maybe he was Johann Heinrich, and when he went to France, maybe he was Jean-Henri. So anyway. Lambert's cosine law, the light comes in, and we keep up with the lighting vector that points towards the light source and the surface normal. We have this angle phi, and how big this angle is affects how much light hits the surface. So if the light source were directly overhead, both the surface normal N and the lighting vector L would be the same. The angle here would be 0 between them, okay? And obviously, if the light is shining directly down on the surface and all the little light rays are parallel because we're assuming the light source is at infinity, well then 100% of the light would hit the surface and be reflected in all directions. But as the angle increases, the amount of light that hits the surface decreases. This is a little less than a 45-degree angle, but at a 45-degree angle, the amount of lighting that hits the surface is only 70%. And then if the sun were all the way down here at the horizon and the angle were 90 degrees, no light would hit the surface. So that is, again, Lambert's cosine law. I think this is where we ended last time. And you can see this is minus L because I'm showing the light rays coming from the direction of the light source. When we're doing the computations, we talk about L, which points towards the light source. So it's the opposite. This is the light coming from the source. This is a vector pointing towards the light source. So this is minus L because if you wanted it to be L, all the little arrows would be backwards, but it would look strange in this drawing. So that's why I'm drawing the light rays hitting the surface and calling it minus L. And you can see, we talked about this last time, as the angle increases, the percentage of the light rays that hit a surface, and these surfaces are all exactly the same length. The way I've drawn them, you can see it drops from 100% to 70% to 0. So how do you get the lighting vector? Well, the lighting vector is frequently given to you. Okay, so like in the math that we're going to do in the model that you're going to actually implement, we just assume that all of our light rays are parallel, and that makes computations easier. But as Eric was asking me after class last time, because that was bothering him, in reality, if this light source is not at infinity, and what is at infinity, right? If this light source is relatively close to the surface, what you would need to do is for every point on the surface, compute a lighting vector. So here's a surface. If this light really were this close to this surface, obviously the point right here, right, the light vector and the surface normal would be 0. So this would be getting 100% of the light hitting this point, right? But this point over here would only be, if we assume this was a 45-degree angle, would only be getting about 70% of the light. And that's why if you think about a light bulb, or Eric was asking about Unreal, when you plop in a light source, right, you get a region that the light source lights up and it attenuates to both sides. Well, that's because it's individually computing the lighting vectors back to that light source because it's not assuming that the light source is at infinity. If you want to do that in your calculations, you could, but it adds a little bit more overhead. And already, I don't know about you, but my computer just kind of chugs trying to get through the number of calculations that we're doing right now. Because remember, we're having to go through layers of software to set a pixel, and normally setting a pixel is a really cheap operation, but because we're using W.fill line and drawing a line 1 pixel in width, that's a horrendously expensive operation, and that's why everything's grinding to a halt. But it's what we got. Okay, so if I wanted to compute a lighting vector for every point on the surface, it would be, you know, end point minus start point. Well, the end point is, of course, the source. The start point is the surface, because this is the lighting vector points towards the surface. So the distance from the source minus the surface, that gives you the lighting vector. There'll be an x, a y, and a z component. Divide that by the distance between those, and that'll give you a unit vector that specifies the direction to the light source. So you could compute it, but like I say here, normally, so if you want to compute it, here are the equations. I even break them out, you know, into x, y, and z. So here's your light source, but it's really at infinity in this case. Well, if it's at infinity, then it doesn't matter what point you are on the surface, because the surface normal, this is flat, it's always the same. So if all your light rays are parallel, you could run through these equations for each point, but they would all return the same answer, okay? But if the light source isn't at infinity, if you're going to model it as at some point in 3D space, then you need to run through these equations to compute the lighting vector for every point on the surface. Does that make sense? And so here, you know, a lot of times I will say something like, the light is entering the scene from a 45-degree angle over the viewer's right shoulder. In fact, this is the description of the lighting environment in assignment 4. And that is modeled by 1, 1, minus 1. You go over 1 in x, up 1 in y, and then towards you 1 unit. And so that'll give you light that's coming in. That'll give you, hold on. That'll give you light that's coming, well, I got to do it backwards, at a 45-degree angle over your right shoulder. Of course, you're backwards for me, so like that, right? So it's it's 1, 1, minus 1. So that's the lighting vector. Okay. And I hope I was in camera when I was doing that. Hell, who knows at this point? It works in class when we're in person. Okay. Okay. So that's the lighting vector. Good. So there's one other thing that we need to think about. Okay. I said we're going to normally cheat and consider this light source at infinity, so all the light rays will be the same, they'll be parallel, so we'll just have one lighting vector for every point source. Okay, fine, we can make that assumption. But if a light source is infinitely far away, Mike, isn't it going to be infinitely dim? Well, yeah, physics, yeah. You want proof of that? Go outside at night when it's not cloudy and look up in the sky. You're looking at millions and millions of suns. But why isn't it blazing bright at night? Well, because those millions and millions of sun, or as Carl Sagan used to say, billions and billions of suns are very, 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 very far away. And so the light is very, 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 very dim. They're little point sources, but they're very dim point sources. Our sun is much closer, so we can still model it as a point source, but it's a lot brighter. So essentially, we generally ignore distance too. So we're making simplifying assumptions here. So we're assuming normally we assume all the light rays in this class, in the programming part of this class, we assume all the light rays are parallel. And we assume that the light has a has a particular constant intensity, okay? So we'll have an intensity at the source, whatever that means, but it's really the intensity of the light that reaches you from the source. And that, again, is usually a constant. Now, you don't have to model it as a constant. You could say, well, you know, if I have the intensity of a light source, right, I know from basic physics that there's an inverse square law, right, that the light spreads out. It decreases as the square of the distance, right, from the source. Okay, you could program that if you wanted to. It wouldn't be that expensive, but people have found that it's really hard to tweak a D parameter, a distance parameter, when you're squaring it. It's a lot easier to tweak a D parameter when you're not squaring it. So normally, if we're going to worry about distance, we normally just say divided by D. And again, physics doesn't work that way. Yes, I realize physics doesn't work that way. We're building a model. We said our model would cheat all over the place. This is just another way that we're cheating, okay? So, and most of the time, in my code and in the code you'll write, we just set D to 1. And that causes the D to be ignored, essentially. So we're ignoring distance. So if you think of the intensity at the point light source, well, since we're ignoring distance, that is the intensity that arrives at the surface. It works good enough most times to produce something that looks reasonable, and that's what we frequently do. So let's put that all together. Computing the diffuse reflectivity for an object, well, it's going to depend on a couple of things. One thing is, the first thing you'll note is I recognize this term because I had it in the ambient term. That's the same thing. That's the constant of diffuse reflectivity. The constant of diffuse reflectivity of the object being illuminated, okay? It's the color of the object, or the grayscale if you're only using a monochrome. And this is monochrome because I don't have red, green, and blue talked about here, okay? So what are these other things? Well, we've talked about phi, right? That's the angle between the lighting vector and the surface normal, so we know what that is, right? We just introduced D, that's the distance. So you're taking all of this stuff and you're dividing by D, which we normally set to 1 if we want to ignore the distance. And this last thing here, this is different. This isn't IA anymore. Remember, we had intensity of ambient light. This is IP. That's the intensity of the light at the point source. Now, again, if D is 1, the intensity at the point source is going to be the intensity at the arrival point on the object. So if D is 1, if you're ignoring distance, you can kind of think of this as, well, you can, if you're ignoring D, you can think of this as the amount of light that arrives at the surface from the point source, because that's what it is. If you're not thinking of it in that way, then you can attenuate it by a distance amount. And again, the models and things like Unreal are use these things, and their models may be even a little bit more complex. But this is in general how lighting works for the diffuse component. Okay, what if I have multiple light sources? Because of course I can have multiple light sources. Then in that case, the diffuse is the sum of this equation for every light source. Well, you have to have the intensity of point light source I times the constant of diffuse reflectivity. Mike, did you forget to put a sub I here on KD? Is that a typo or is that not a typo? Because everything else in this equation has a sub I. Well, what are these other things? Well, cosine phi sub I is the angle between the lighting vector for light source I and the surface normal, and D is the distance to light source I. So I come back to the question, did I forget to put an I here on, should that be D, K sub D sub I? Somebody's got to answer that. Yes or no? Did I make a mistake there? Come on, somebody. Don't disappoint me. If you have no idea, then you're lost in my lecture, and that'll make me sad, and I'll start crying. And you don't want to see a 60-year-old man cry. It's depressing. Come on, people. Am I going to have to start randomly calling on you guys? Has everybody fallen asleep? Let me check out everybody here. I see people looking. That's good. There are 15 of you here, and most of you have your cameras on, and y'all look awake. So does Eric? I'm going to ask you. Just I'm going to pull you out of the crowd and force you. Should the KD have a sub I on there? You're muted, by the way, Eric. Unmute yourself. We're having a conversation here, my friend. Okay, Eric.
I'm sorry.
So what does KD stand for?
It's the constant of diffuse reflectivity.
Okay, and you've said a lot there, right? It's the constant of diffuse reflectivity, and is that a characteristic of the lighting environment, or is that a characteristic of an object?
It's the characteristic of an object.
Of an object. And so if we're talking about, so you've answered the question there, because if we're talking about, if we're talking about lighting in the environment, the KD is a feature of the object. And it doesn't matter. I mean, you know, we were talking about my pasty white skin last time, or modeling whatever pinkish color you want to, you know, call this. How it looks will differ depending on the light sources and all of that, but the actual inherent pigmentation tone of my skin isn't going to change. And certainly it isn't going to change per light source. So no, I didn't leave off an I. The object isn't changing here. It's the object has the same color, right? You do need sub I's on the intensity of point light source, because if I've got 5 point light sources, I've got the intensity of point light source 1 and 2 and 3 and 4 and 5. Each of those light sources will be lit from a different angle, right? So the angle between the surface normal and each of those lighting vectors will be different, and we would imagine that each of those lighting sources would be at different distances from us. So everything in here needs to be sub I except the constant of diffuse reflectivity. It doesn't change from light source to light source. Okay, let's see. And if I had read Stephanie's comment in chat, that worked. Maybe you should have read that, Eric, and you'd have been a lot more comfortable. And again, because of that, you can look down here and I can pull that KD out of the summation and just multiply it here. Instead of multiplying the constant of diffuse reflectivity individually times each of these things, I can compute the whole sum and then multiply it by the constant of diffuse reflectivity. Does that make sense? I see some nodding heads. Okay, good, good. Okay. Nodding heads are good heads. I also see only 15 people in here. And of course, that's good because there are 15 people who, like I said, half the class, there's 21 people in the class, or 22, 21 people in the class, and I had 10 people who scored A's on the programming assignment. I would bet that those 10 people are here. I would also suspect that most of the people who did very poorly, and there were a couple, there were more than a couple, there were about 5 that did pretty poorly, I would suspect that they're probably not here. There might be a correlation between those two things, you think? Okay. All right. You can lead a horse to water, but you cannot make him drink. Okay, so this is the monochrome model, right? How do we compute the cosine of the angle? Well, we already know that because we learned back when I was talking about the basics of vector math that P dot Q is equal to the magnitude of P times the magnitude of Q times the cosine of the alpha, the angle between P and Q. Well, if you take P and you take Q and you make them unit vectors, which means they'll have a length of 1, then P dot Q equals 1 times the cosine of the angle. 1 times 1 doesn't do anything, so P dot Q is the cosine of the angle. Or you can say it backwards, the cosine of the angle is P dot Q. So that means that you can just do a dot product. So to get the cosine of the angle phi, that's the angle between N and L, you just go N dot L. And if you're still having a little bit of problems with vectors, I remind you here that N is actually 3 things. It's an X, a Y, and a Z, like L is 3 things, and this is how you multiply it out. So we can restate our diffuse equation by removing cosine of the angle and replacing it with N dot L. And again, how do you calculate N dot L? It's actually those 3 little calculations there. So we now have, we can now move on from a single source to a multi-source. And so the diffuse reflectivity for multiple sources is this, for source I to N. And again, before I break it out, right, the I, the L, and the D are subscripted. The N is not subscripted. Why isn't the N not subscripted? Because it's the surface normal. The orientation of the object in space is not dependent on the light sources, obviously. So there's no sub I on the N. Your surface has one normal, and that doesn't change in any way depending on the light sources. Now you might say, well, this is constant, can't I pull it out? No, because remember, it's got to be multiplied dot product to the L's, the lighting vectors, and every light will have its own lighting vector because the lights will be in different spots. Again, you know, here's the longer version where I plot out what N dot L sub I actually means, and I do a little example here. Where you have an N of 0, 5, 0, that is just a normal that points in the direction of positive Y. So our plane here would be in the XZ plane. Our polygon is in the XZ plane, and the surface normal is parallel to the Y-axis. Our lighting vector, this is a little bit simplified from what I was talking about before. The light is, the z-axis is 0, so the light is in the xy plane over x1 up y1. So it's at a 45-degree angle, but the light is in the plane where z equals 0. And so if I have an intensity of half and a constant of diffuse reflectivity of half, and I set my d of 1, I'm going to ignore the distance. How do I put all this together? Well, I need to normalize these puppies because these aren't of length 1 yet. So first thing you do is you normalize your normal and you normalize your lighting vector. So now our normal is 0, 1, 0, and our normal vector and our lighting vector is 0.7, 0.7, 0. Plug those puppies into our diffuse reflectivity. This is a monochrome single source because I only gave you one source. Plug them in, do the math, and you come up with 0.17675. Scale that to 0 to 255, and you come up with 45 or 2D. And that's the color. You might say, but wait a second, it's 24-bit color, you only gave me 8 bits. Well, yeah, I only gave you 8 bits. You can put that 2D in red. You can put it in green. You can put it in blue. You could put it in all 3 of them if you want it to be a grayscale. So yeah, I'm computing one intensity, but what you do with that intensity, as far as what color channel you put it in, or whether you put it in all color channels, is up to you. Okay, and so now we can say, well, I don't have the whole model yet, because our whole model is, remember, ambient plus diffuse plus specular, but now I've gotten through the ambient and the diffuse, so I could put them together. So the intensity of ambient plus diffuse is this. I put the original equation in green, and I put so that's the ambient part, and here's the diffuse part, the point diffuse in blue. I could do it for I can rearrange things a little bit by pulling out the constant of diffuse, right? And if I do, instead of a single emitter, I can do multiple emitters there. So we've got our little eyes underneath everything. And if I want to do it in red, green, and blue, I repeat it 3 times. Would it make sense to just multiply the base color by that intensity? What do you mean by the base color, Eric? Audio might be easiest.
I mean, like if the polygon was already colored and you were just trying to like know what color you need to make it after it's being lit, would you just multiply the color?
Yeah, you could do that. You could do that. That would and in fact we really are doing that, because that's what this KD red, KD green, KD blue is. That's the red, green, blue of the color. So if I had a yellow object, right, that was like a fairly bright yellow object, this might be 0.75, 0.750. So the equations are doing exactly what you're asking to do. Do you see that? Yes, no, maybe? Okay. All right. All right. Blah, blah. These equations are only good for cosine of phi being less than or greater than 0, greater than or equal to 0. Because when the cosine of phi is greater than or equal to 0, then the source is lit from above. If this thing comes out to be negative, right? If your n dot L gives you a negative number, it means that you're being lit from below, and so normally that's not going to do anything because the light source isn't hitting the surface that you're looking at. And so in that case, we can set the diffuse to 0 for the lighting there, since it's being lit from below in that case. Also, you notice I said as long as it's, these are fine as long as it's greater than or equal to 0. Well, when it's equal to 0, your diffuse is going to mathematically work out to be 0 anyway. So, okay, specular reflection. We're getting there. Since we are lighting from the right, will the left sides of our objects be black? Okay, that's a good question, but I'm going to throw that question to the class. Andrew's asking, since we're modeling with our light coming in from the right, I said over my right shoulder coming in at a 45-degree angle. Andrew's asking, will the left sides of our object be black? Yes or no? Let's take a poll. If Andrew had asked you that question, how would you answer it? Eric says it wouldn't be totally black because of ambient lighting, and that is absolutely correct. The ambient component is providing some background lighting, so it won't be totally black. If we go back and look, again, I'm going to have to scroll. I'll try doing it this way, but I know I'll miss it. This puppy, right? We haven't covered the specular part yet, but we've covered the diffuse and the ambient, right? This is backside. None of the point light is hitting back here because this is on the back side of the sphere. But it's not black, it's dark red. Why is it dark red? Because the ambient component is providing that general background lighting. Okay? All right. Okay, specular reflection. So far, the light that's hit us, we've said, oh, it goes out in all directions. And so this is diffuse reflection. This is what we just studied, right? Now, this is minus L because I'm showing the light ray coming from the light source. If it were going this way, it would be L. But the light that hits us goes out in all directions. So this is diffuse reflection. And we ambience the same way, only the light's coming in from all directions, but it's still going out in all directions. So everything we've looked at so far is diffuse reflection. The light that gets to us goes out in all directions. But some objects have a shininess to them, like that red sphere that we just looked at a second ago. It had a highlight on it. So how do you get highlights? Well, you get highlights through specular reflection. And basically, there's going to be a term. We're going to call it, and a lot of times the term is N, but N is such an overused variable. I'm going to call it spec index because that's what it is. It's the index of specular reflectivity. So spec index. Spec index is going to tell us how shiny a surface is. Now, a surface may be very shiny, or it might be quite dull. And if it gets dull enough, there's not going to be any specular reflectivity. But even something like cardboard, right, usually has like some wax impregnated on it, some sort of a waxy surface. So cardboard has a little bit of sheen to it, depending on the cardboard, I guess. You know, metals are much more shiny. That's why we like them, because they look pretty, because they have these pretty little reflections on them. All the way up to, you know, glass and water can reflect. So in specular reflectivity, you've got the light coming in, right, the lighting vector pointing out, whichever way you want to think about it, and you've got a mirror direction, a reflection direction. And so what happens with specular reflection, the light comes in and it bounces off towards a mirror direction. If the object is not very shiny, so it's got a small specular index because it's not very shiny, it's getting closer to waxy cardboard or maybe even unwaxed cardboard. So the smaller the specular index gets, the less shiny the object is, and the wider the range of angles that the reflected light is reflected. The larger the specular index, the more shiny the object is. And so the light rays are focused more compactly around that reflection direction. Okay? So that makes sense. If an object is not very shiny, whatever light hits it is going to be closer to diffuse. It's going to spread out more. If the object is very shiny, has a large specular index, the light's going to be concentrated around the mirror direction or the reflection vector. Does that make sense? So the spec index is saying how glossy or how shiny it is. It's not very shiny, not very glossy. Light's going to go out in a lot of different directions. Eventually, it'll get down to just being the same as a diffuse reflection. If it's very shiny, the light's going to be concentrated around the reflection direction. So a high specular index would create that small, bright highlight like in the example. Exactly. But a low index, it'd just be kind of brighter on one side. Absolutely correct. And we'll show examples of that, but you're on the right page there, Eric. Okay. Now, the model that we're going to look at is called the Phong illumination model, sometimes called the Phong reflection model or the Phong illumination reflection model. And like I said, in Phong, a lot of times if you're looking in the literature, they'll talk about the specular index as being n, but again, that's an overworked variable, so I'm calling it spec index. Takes more characters to write it, but it's a lot more clear on what it is. Okay, so here are the two paragraphs where I go back through what a small specular index. Well, a small specular index, it's not very glossy, so the light goes over a wider area. Now, as the specular index approaches 0, the surface becomes less and less glossy. We can see the highlight over a wider and wider area, but in reality, that highlight would be dimmer, right? Until eventually, when spec index becomes 0, the surface is a perfect diffuser of light. So you're back to diffuse reflectivity. A large spec index is that you got a very tight, a very tiny, but quite bright highlight, right? Now you might think, I make a little comment here that as the specular index approaches infinity, shouldn't light be exactly on the mirror direction? And if that's the case, wouldn't this thing actually be a mirror? Wouldn't you see reflections? And the answer to that is no. The Phong illumination reflection model can't produce reflections. It would just turn out to be white, is the way Phong would render that. But we'll use another technique later on in the last few lectures where we talk about ray tracing, and that'll be your last program. Okay, so the reflection vector, you might say, well, that's just minus L, right? It's not going to be that. But we can say that the angle between the surface normal and the reflection vector is the same as the angle between the surface normal and the lighting vector. So that's our reflection vector. And I haven't yet told you how to compute R. Oh, don't move R, Michael. I haven't told you how to compute it, okay? But we will a little later on. But to continue, there's one other thing you need. You need a view vector. So to compute Phong, we need a bunch of vectors. We need a lighting vector, a surface normal vector, a reflection vector, and a view vector. We have to know where the viewer is in space relative to this whole system here. So we have 4 vectors, L, N, R, and V, and we have 2 angles. We have phi, the angle between the surface normal and the lighting vector, which is the same as the angle between the surface normal and the reflection vector. And then we've got another angle, theta, between the reflection vector and the view vector. In other words, light in Phong is going to come in and bounce off in a particular direction. Well, if I'm way over here, right, looking at this surface, I'm not going to see this reflection because I'm nowhere near it. But if it's coming in and going here and my eyeball is here, or even if my eyeball is over here, right, this angle is going to be pretty small. You can see what I'm trying to show here. So I'm as long as I'm near the reflection vector, I'm going to see that highlight. So I have to know where is Mike. Find Waldo. Find Mike. Right. And the way we've modeled things, the view vectors has always been fixed at 0, 0, minus 1. It makes it easier. There are certain things I have to throw on the floor. And so we don't really worry about a viewpoint being somewhere in 3-dimensional space. Our viewpoint is always at 0, 0, minus 1. Well, that's the vector that points towards the viewer. You can set the viewer up to be anywhere, but when you go to actually do the projection, you have to go through all those equations that we covered a long time ago about rotating around an arbitrary line in space to line up this line with the z vector is what you have to do. So you basically have to rotate everything in the world through those equations. Now, of course, you don't individually rotate everything. You come up with a composite matrix and throw things through that to get the orientation before you do the projection. But we've discounted that. But even if V is fixed at 0, 0, -1, this plane here, right, that the reflection is in could be at any orientation to your eyeball, right? Because objects can be at any arbitrary orientations. So I still have to worry about the angle between my view vector and my reflection vector, even if my view vector is always fixed at 0, 0, -1, because the reflection vector certainly isn't going to be fixed. It's going to vary. Another thing here that I try to make clear is that N, L, and R are in a single plane. The light rays come in, they bounce off, and they bounce off in the same plane. So phi is in the plane of L and R. Okay, so the angle here between N and L is the same as the angle between N and R. But this theta between V and R, V is not, it can be in the same plane. I could be right here, my eyeball could be right here, looking directly into the reflected light ray, but almost never is that the case because the view vector is independent from the orientation of the polygon. So I tried to show it can your eyeball can be anywhere in relation to the reflection vector. So this angle theta is in a different plane than this angle phi. That's going to complicate things a little bit because you can't really derive the angle theta here from L and R. You're going to have to take the view vector into account as a separate calculation in a separate plane. We'll get to the details. So, what is the Phong specular reflection equations? Well, specular is modeled as IP, that's the same intensity of point light source, times Ks. This is a new constant. It's the constant of specular reflectivity that's telling you how shiny is the object. So we have Kd, it's color, it's general color, right? Kd red, Kd green, Kd blue. But we also have the constant of specular reflectivity. How brightly does it reflect incoming light? So you need to know the intensity of the point light source, the constant of specular reflectivity, and then the cosine of theta. Remember, theta is the angle between R and V, right? It's the cosine of the angle between R and V. So if R and V are unit vectors, you could take the dot product and you raise it to the power of the spec index. Okay, why are you raising it to the power of the spec index? Let's think about, does this math do what we want it to do? Okay, so the first thing is, if R and V are identical, if my little eyeball is right here, okay, so I'm looking directly into the reflected light, okay. In that case, it doesn't matter the spread of the light because I'm going to see the entire specular highlight. So when R and V are identical, that is when the angle between theta, between them, the angle theta is 0, and thus the cosine of 0 is 1, then the spec index is ignored. So if I'm looking directly at the reflection vector, I don't care how much it spreads away from that reflection vector. I'm looking directly at it. So I'm going to see all the light anyway because there's no deviation between me and the mirror direction. So spec index gets ignored in that case. Well, why does it get ignored? Because 1 raised to any power is, of course, 1. So when r dot v, or the cosine of theta, is 1, it doesn't matter what your spec index is, because this term is going to be 1. And that means the specular reflectivity is just going to be the intensity of the point light source times the constant of specular reflectivity. So when this angle, theta, is 0, right, which means that the lighting vector and the reflection vector, they are identical, right? So that'll give you a 1. Then it doesn't matter what the spec index is. It's essentially ignored, and the equation simplifies to that. So essentially, it becomes another kind of ambient lighting, if you want to think of it that way, right? Because that equation is very similar to the equation for ambient lighting, except now I'm taking in point light source rather than ambient light source, and I'm using the constant of specular reflectivity instead of the constant of diffuse reflectivity. So when the angle is 0, cosine of the angle gives you 1, and it doesn't matter what the spec index is, because all of this is going to be 1. So you're going to get 100% of the light from IP times KS. Okay. Now, what if the spec index is 0? Okay. It's as tiny as it can get. Now, remember we said the spec index is the glossiness. So a very low specular index is something that's not very glossy. And so the less glossy you are, the more spread of that highlight. And taken to its extreme, that highlight is spread in all directions. So you get another diffuse component. Well, that happens when the spec index is 0, because anything raised to the 0 power is 1, right? Anything raised to the 0 power is 1. So if this is 0, if spec index is 0, it doesn't matter what the cosine of the angle is, because the light's going to go out in all directions equally. So again, when the spec index is 0, you revert, back to this. You're going to get 100% of whatever light there. It just becomes another ambient component. And notice I'm saying it's another ambient component because we're not using Lambert's cosine law here to attenuate based on direction. You might say, well, shouldn't you? Well, probably, maybe, but it's a model, and we use the model because the model kind of works, and it's the accepted model. Okay, so now what about spec indexes that are greater than 0 when theta, the angle between the lighting vector and the view vector, is not 0? So in other words, the general case where this angle theta is not 0, okay? Let's say, in fact, though, that we're going to fix it. We're going to say, let's look just at this case, or let's look just at this case. Let's look at a case where the angle between the reflection vector and the view vector is fixed. Okay, so we're going to look at a case where the angle is fixed, and then we're going to ask ourselves, what happens if we change our spec index? Well, as the specular index goes up, gets to be a bigger number, the light rays are going to be more and more compressed around the reflection vector. There will be less spread. And that will mean that as long as this angle here, theta, is not 0, that the amount of light hitting your eye is going to drop, is going to decrease as the specular index increases. That always seems backwards to students, but it's not backwards, because the specular index says how shiny the object is, how tightly the light rays are around this reflection vector. And if theta here is fixed at some angle greater than 0, as when it's dull, they're reflected around a pretty big area, and a lot of it might fall on my eyeball. But as we get to higher spec indexes, the spread's going to be much tighter, so fewer light rays are going to reach my eyeball. So as the spec index goes up, the amount of light hitting my eye goes down as long as I'm not looking directly at the view vector. When I'm looking directly at the view vector, it doesn't matter what the spec index is because I'm on the mirror direction and I'm seeing 100% of the reflection. Okay, Mike, let's see if you can scroll back down here. Does that make sense? Well, it does, because let's look at the math. As the spec index, I said, let's fix, and let's say that I'm at a 45-degree angle between the view vector and the reflection vector. So I'm going to fix that at 45 degrees. Well, when the spec index is 0, we said it doesn't matter what the angle is, because it's always going to be 1. 100% of visible light will be at the viewpoint. When the spec index is 1, you'll see 70%. When the spec index is 2, it's 0.7 squared, which is 49%. When spec index is 3, you're cubing that 0.7, so you're getting 0.343. The amount of light that is hitting my eye is going down as the specular index increases, because my eyeball was not looking directly at the reflection direction. I was somewhat off the reflection vector. I was in a state like I show here. And so for a fixed theta, 45 degrees in the case of the map that I was giving you, the amount of light that hits my eye decreases as the specular index increases, because the light, as the specular index goes up, is being more and more closely concentrated around the reflection vector. Does that make sense? Please ask a question. So we can expand this to red, green, and blue. Nothing changes. I just now have 3 copies of the equation. We can expand to multiple light sources in the monochrome. All you do is you subscript the intensity of the point, and you subscript the angle, because every light source is going to have its own reflection vector. You can pull out the Ks, because the constant of specular reflectivity does not depend on the light source. And finally, you can put it all together to get the multi-source RGB version, where you've got the 3 equations, red, green, and blue, and you have the multiple light sources per equation. And that gives you specular. The last thing we're going to have to do next time is on Monday is compute the reflection vector. I didn't show you how to do that yet. So I've given you all the equations, and you see that you're going to have to use the reflection vector, but I haven't told you how to compute that yet. We'll compute that next time, and then I will work through an entire example where I'll give you the code. It's called the 20 spheres example. We will show the actual code for implementing the lighting model. That'll get us almost to where we need to be to start working on the programming assignment. The programming assignment will then take that lighting model and apply it to a polygon. And we haven't talked about how to do that yet. Any questions before we call it a day? Hopefully you guys have a good weekend, because you don't have a programming assignment to worry about this weekend. Any questions for me, my friends? Well, okay, I'm going to stop the recording. You guys have a good weekend, and I'll see y'all later. Bye-bye.